I guess we can get rocking and rolling. Well, good morning. Welcome to the second Steiner Tech Talk. This will be the second iteration we've had, and hopefully more to come once every month. I myself, Rob Elliott, Senior Director of Category Management Marketing, and today we have John Redeman with HOFFMAN, kind of going over the topic of heat in cabinets, so hot cabinets, hidden risks, thermal audits, and how important they are. Thank you for joining us, John. From a Steiner Tech Talk standpoint, again, monthly series, trying to connect just global experts, people that have a lot of insights and innovation and solutions, wide range of topics. We will have a whole bunch of different segments we're going to focus on, from commercial construction, machinery OEMs, industrial end users, and even part of our metalworking group that we had last time on safety. And also, all of these recordings, if will be available on our Steiner website. So hopefully, add a little bit of picture there. It's under events and training. You can see Tech Talk there. We do have it posted on YouTube as well, so people could go back and review it as need be. So today, John, welcome. I don't know if a little bit of your background, if you want to go ahead and give a little bit of your background on who you are and how you got here, and a little bit of your expertise, and we'll kind of dive into it from there.
Fantastic. Thank you, Rob. Appreciate the opportunity to talk to everybody this morning. I am John Redeman. I'm the Western Regional Sales Manager for HOFFMAN Cooling Products. It's primarily all I focus on. What I know about an enclosure is that my stuff bolts to it and it cools it. I've been with HOFFMAN for going on 18 years. Prior to jumping into the wonderful world of sales, I was the global director for our aftermarket services group for about 5 or 6 years. And prior to that, I have about a 34-year career history in HVAC. It's pretty much what I've done most of my career is residential, commercial, industrial. I've had my own business in Minnesota for about 7 years, where I've performed all of the design functions, installation on gas, refrigeration, electrical, as well as ducting, service work, universally certified refrigeration, carrying my certified energy manager license, Minnesota indoor air quality certified. So what I know about boxes is we do a really good job of managing heat in them. So if we have challenges, I like to chase after those and help you guys out. So again, appreciate the opportunity to talk to everybody this morning.
Well, it seems like you got a lot of good background and experience to be able to talk about this today. So moving on with the presentation.
Let's dig in.
So just kind of one of those things that I know over the course of my career, I've been walking around and all over the country, and these pictures right here kind of truly resonated, because I'm sure all of us have seen it. And thinking about what time of year we're in, I guarantee you there has to be 1 or 2 cabinets in everybody's location that look exactly like this.
Yeah, so believe it or not, we do see this a lot more frequently than we might think, right? And what we're seeing here are our customers are scrambling to try to keep their production up and running. They're at a state where a cooling system wasn't properly planned, and it's caused downtime. And these are the last ditch efforts to get them back up and running, right? Because it isn't the cost of the cooling system that we're concerned with as much as the cost of the lost production.
Right.
So when we're talking about climate control solutions and thermal management, what the importance of it, and what are some of the challenges, and really how do we approach it, right? What are sources of heat, and what is the proper way to cool an enclosure, and some of the options methodology available to us. How do we determine what we would use in an existing system and thermal audit service really helps guide us. And we've got some online tools that really guide to the proper selection of what that, potential solution might look like. And then as well as, the after sales support, which I think is critical. If there is a challenge in your facilities, what do we do, and what tools do we have in place to help support you guys, right? So we'll do a high level review of each of these topics. Next slide. So some of the challenges in maintaining, enclosure temperatures, and everyone asks, what is the ideal temperature? And for standard industrial automation equipment, we really like to operate an enclosure between 85 and 95 degrees Fahrenheit. Now that sounds kind of warm until I start to explain it, right? We don't want an enclosure to be what we used to refer to as beer can cold. And the reason we don't want that is because we have a sealed system, and if we run that enclosure too cold, we'll create surface areas that we will condense on those areas. And those areas would include all of the printed circuit boards of all of your components. So when we condense, we create flash condensation that potentially could short these components out. And if not short out, we start to cause flash corrosion on those components. So ideally, we want to run our enclosure temperature above our condensing temperature, our dew point. And an 85-degree temperature will get us above that. So we'll run it warm enough to avoid potential condensation issues, but cool enough that we won't affect overall reliability. Now, when we're trying to manage these temperatures, we have to, be concerned with heat buildup, potential inadequate airflow, right? Some of our components have fans in them, and if we're blocking off airflow, or if we have an extremely massively dense density or populated enclosure, that can complicate the thermal management of that system. Next slide, please. So when we're looking at managing the thermal load of an enclosure, we have three potential heat sources. We have the components inside the enclosure that are potentially a source of heat. And we have if our ambient temperature is higher than our desired enclosure temperature, then we have that external ambient load onto the enclosure as a second heat source. And if we are outdoor in direct sunlight, that solar load would be a third source for us, right? So the location of an installed system, whether it's next to, an oven, in a foundry, next to a kiln, any type of process that could potentially produce heat, that would be a source, an additional source of heat for us. So when we're looking at managing the overall load, again, that is an overall load. We have the internal, and then we have the ambient, and if we are outdoors, we have to consider it being in direct sunlight as well. There are different ways that we can help mitigate the load as we start to navigate through the application.
Yeah, and yeah, I was just thinking my God, how many NEMA 3R enclosures have you seen out there driving along or out there in a field and a part of a process? I mean, those are out there very often just baking, and standard NEMA 3R enclosures, allow for that seepage at the bottom, but there's really not a whole lot of additional cooling that go along with it that probably could definitely affect the process.
Yeah, exactly. And an ANSI 61 gray enclosure in direct sunlight adds about 30 to 40% to the solar load of an enclosure as compared to a light colored or a white enclosure, which could definitely affect the overall sizing of a system, right? So,
Yep.
So thank you. That's absolutely critical. When we're looking at internal heat loads, these are all of the things that we're familiar with, right? Variable frequency drives, servos, PLCs, even the motor starter, believe it or not, that has a heat load to it. Not only as that motor is starting, but once it's across the line, there's still a residual heat load being put off from the starter. So there are some sizing exercises that we do when we have larger horsepower starters. Power supplies are very similar to transformers. Essentially, it is a transformer, so the efficiency losses in a power supply will be calculated like they would a transformer. Terminal blocks, indicator lights, and very minimal, but still, potential heat sources. And as we populate these enclosures, especially now, we're seeing much higher densities and much smaller enclosures, which is leading to much higher heat loads. That once we close that door, we are capturing all of that heat inside of that enclosure, which is driving the internal temperatures much, much above what ideally we'd like to see, right?
Yeah. Well, and also, I mean, you used to see, depending on the generation of the VFD or the soft start or whatever, there's also spacing that you have to have between the units, just for that airflow and that cooling. And a lot of times, like you said, people just want to, in control camps, try to put as much density as they can because they want to make the overall size of the enclosure smaller. But like you said, like that they could have additive effects because you could have that unit on the side adding more heat to that component, and that's just generating more heat inside the enclosure.
And something to really take into consideration is if you look at the size of a 10 horsepower drive from even 10 or 15 years ago, as compared to the size of a 10 horsepower drive today, it was much larger than it is today, right?
Yeah.
Yes, it is different technology today than it was 10 years ago, but you had more surface area to help dissipate heat off the components from the older drive as compared to today's drives. We don't have the surface area to help dissipate the heat away from the IGBTs and the other components, making it more critical for spacing, following spacing requirements and managing that internal heat load. I see a lot of upgrade installations where previously didn't require a cooling solution, but now because we're packing a lot more in, we're like, we have this big box, we can put more stuff in there. And with the lack of the surface area on the specific components, it's leading to needing cooling systems. A great example is a solid state relay versus the old cube relays. The old cube relays that everyone's used to didn't really produce any heat, but a solid state relay, if you're replacing from a cube to an SSR, will produce between 1 to 1.5 watts per amp going through the relay. So if you had a 30 amp cube relay, didn't produce any heat, we now have a 30 amp SSR, we've now got between 30 to 45 watts of heat. So if you have an entire bank of relays that have now been upgraded to SSRs, that's fantastic. But that's some additional heat load that we have to take into consideration as we upgrade these panels.
Yeah, I just something I would have never thought of. I mean, but it makes a lot of sense.
Sure. Yeah, next slide, please. So when we're talking the importance of managing the heat loads in the enclosure, all of our components have a maximum temperature rating to them. I'll take a drive, for example. You'll see a drive rated at 50 C with potentially a 15% B rate. That doesn't mean that we can operate at 50 C on a continual basis. The ideal temperature range for an industrial automation enclosure is really between 85 and 95. UL says that we can go up to 104 for design temperature before we have to submit for variance, right? And typically, if it's simply a drive cabinet, I think that drives are a little bit more robust than your electronics, PLCs, power supplies, network switches, things of that nature, right? Those typically I calculate at 85. But this example here, so for every 10 degrees C or 18 degrees F above room temperature, you cut the life expectancy of your components in half. And that's linear, as you can see. So for every 20 C or 36 F, you would cut that in half again. So if we have a drive that's rated at 50 C and we're operating it at that condition consistently, we won't get that, let's say, expected 10-year lifespan. we'll get about 2.5 years off of that drive, right? So managing the internal heat load and the temperature inside of an enclosure is really, really critical for the overall life expectancy of those systems. Um, and it really becomes conversation around uptime. How can we implement systems to help keep all of your systems up and running? So, you guys can produce the products that you produce. Uh, Next slide, please. When we're talking about cooling an enclosure, there are three basic ways to cool a system, and that is through a sealed enclosure, fresh air cooling, and conductive cooling. And a sealed system essentially is just that, and that is that the enclosure air does not interchange with the ambient air at all. It just simply recirculates inside the enclosure. Fresh air cooling is literally using the fresh air like a fan and filter system, and we're pushing it through the box, whether we push it through or we pull it through in a vacuum. There are, different reasons based on application and why we would do one over another. But essentially, we are using our ambient air as our cooling medium to help manage that temperature. And then we have conductive cooling, using the enclosure surface itself to help us dissipate the heat. Thermodynamic law, hot goes to cold, right? So hot will transfer to cold until it can't transfer anymore. Next slide, please.
Yeah, and I'm sure, like, based on the environmental conditions and what you have going on, to your point, fresh air cooling, what's the ambient temperature coming in, you're only going to get so much effect. And even it seems like the conductive cooling tends to probably be the methodology most people use right now.
Yes, thank you for that, Rob. I have a lot of conversations with customers where they like to try to incorporate conductive cooling to minimize additional components, fans, filters, heat exchangers, air conditioners. And we have an online sizing selection program where we can run different scenarios to see how large of an enclosure we would need to dissipate 500 watts of heat. When we're talking cooling, we have passive systems and we have active systems. A passive system means that our enclosure temperature can be higher than what our ambient temperature is. And that general rule of thumb is 10 degrees. Okay. An active system means that we need to actively drive our enclosure temperature below whatever our ambient temperature is, right? So a sealed enclosure cooling has both active and passive. Fresh air cooling is passive only, and conductive cooling is considered passive only. The fresh air, let's say we have 75-degree fresh air that we're pushing through an enclosure, the best that we will be able to expect in that enclosure would be 85 degrees. Depending on how much air we push through, would be 85 degrees. Conductive cooling, again, approximately that 10-degree delta, depending upon how big we make the enclosure, right?
Sure.
And with the sealed enclosure systems, we have an air-to-air heat exchanger, which is also passive. The only difference between the air-to-air heat exchanger and the fresh air fan filter system is that we are recirculating enclosure air and we're keeping the enclosure sealed as compared to pushing air through the enclosure. So if we have highly contaminated air, but it's at a good temperature, we would use an air-to-air heat exchanger and keep the enclosure internal sealed up. So we're not pushing those contaminants into the box.
And I think one of that consideration or the point that you made earlier about just trying to maintain that 85 temperature, it's not like you have to slap on this huge gigantic air conditioner to kind of get that optimum operational temperature. So it's not like bigger is always better, like you said, the condensation. So, as you move forward and think about it, maybe, sometimes smaller actually is better based on what you're trying to achieve. So, you don't always have to slap this huge air conditioning unit on it to make it work.
That's a great point. That actually is the worst thing that we can do in this scenario is put the largest system on that we can. Because ultimately what happens is these, we have a heat load in a fixed space. And if we put too big of a cooling system on there, too big of an air conditioner, we will promote short cycling within that air conditioner. And we will start to burn through the life cycles of the components within the air conditioner. Air conditioner is an electromechanical device, so we have, we're limited in our life cycles. Every time we start and we stop, we're going through a life cycle. So, if we have an air conditioner that's 2 to 3 times larger than needed, it will cycle 2 to 3 times more frequently. Therefore, it will fail that much more frequently.
Okay.
Right. So, thank you. So, kind of touched on this. Traditional methods of cooling are fan and filter systems, heat exchangers, air-to-air heat exchangers, and then, air conditioning systems. There are air-to-water heat exchangers where we would tap into the process water or a chiller, and that would become a active cooling solution. Where we would provide chilled water to a heat exchanger, cycle that through the heat exchanger, and able to provide cooling for that enclosure. Now, they kind of jumping ahead a little bit. Water cooling is extremely efficient as compared to air cooling, right?
Yeah.
Whether it's and when you're looking at a chilled water system, water has a 25 times greater ability to transfer heat than air does. So we can get a much higher cooling capacity in a much smaller footprint using an air to water heat exchanger, but we need to have chilled water supply available to us, whether that's through plant process or through an industrial chiller. Um, that's the caveat, right? And we do have to get that piped into the system somehow, where air-to-air heat exchanger, air conditioner are standalone systems. Next slide, please. So we kind of talked about this, closed loop versus open loop, where we're just recycling enclosure air. We don't have any interaction. And then open loop is just essentially using the cooler air as our cooling medium to manage our overall heat loads. And that 10 degrees is the general rule of thumb. Now, the higher the delta, the smaller the cooling solution, right? If I have, example, if I have 75-degree air and I can maintain an 85-degree enclosure at say 400 CFM requirement, 65-degree air, 85-degree enclosure, so I now have a 20-degree delta, I would only need approximately 200 CFM.
Cool.
So as we increase in delta, our cooling requirement starts to decrease. And then at some point, as that delta increases, the higher the delta, we may get to a point where all we would need is just the enclosure itself to conductively cool it for us.
So definitely a lot of variables in there to help you figure out what the right solution is.
Yes, and the online selection tool really does kind of walk us through it in a very simple format. Jump to the next slide. Touched on this 25 times greater, so we can kind of skip past this.
Yep.
The thermal audit is a great way to help you guys identify where we're potentially having issues and avoid those shutdowns, right? We go into a facility and really what we're looking for is the enclosure size and what the ambient temperature is and what that enclosure temperature is while that process is running. We're looking for the difference of internal temperature versus ambient temperature. And through the selection process, we can estimate how much heat is being produced and come up with a potential cooling solution. To Rob's point earlier, not everything needs an air conditioner, where we may simply be able to use, plant air and push it through the system to very cost effectively manage that thermal load for that application. or, by going through this process, we can also estimate what the actual maximum temperature could get to help you make some decisions on, potentially avoiding potential shutdown or premature failures within your applications.
Yeah, and maybe we can kind of, I mean, how often do you recommend doing a thermal audit? I mean, obviously you need to have a baseline and some way to track that process. And, I mean, but is this once a year thing, once every other year, or is your answer, it depends on the environment you're in?
Well, I would say that once you do a thermal audit on an enclosure, and you've identified a potential issue, right? Then let's say we address that challenge and we put some solution on there. It wouldn't hurt to readdress that at a later point in time. But if a panel has been upgraded, would be a great time to do an audit. Anytime a new panel has been installed would be also a good time to do an audit. Don't always assume that because it's a new machine that the calculations are done correctly. We see a lot of new installations there where, I guess I hate to say this, but costs were cut or there was a miscommunication in application. So maybe not the proper temperature profiles were used during the initial design phase. But it's good to do an audit, especially if you're experiencing potential premature failures, right? If the enclosure uh, temperature is managed properly or the enclosure heat load is managed correctly, you should see 10 years out of your components. If we're seeing premature failures, that is a prime candidate for an audit.
Yeah, and I think even a little bit of risk mitigation, like you said, you install a new machine in there, it's been running for maybe 3, 4 months just to do a quick audit, maybe at this time of year or something that's in a high heat process, just to kind of do that a little bit of a double check. Maybe that kind of prevents a problem before it happens. And like you said, do an audit once you see some failures, but thinking about that last chart of the degradation of life that you get out of your component long before it may be a brand new piece of equipment, but getting ahead of it now may lead to a lot longer uptime in the future.
The thermal audit really is designed to help avoid the failures.
Yeah.
Yeah, it's really designed to minimize that downtime. Regular maintenance, just like your car, needs to have the filter changed. Fans, filters, heat exchangers, air conditioners, they're pretty maintenance free. But they do have filters that we do need to change periodically. And the environment is really the determining factor in how often we do that. Some environments we can do once, twice a year. Other environments we have to do monthly. I would say quarterly would be a really good time interval. Is just change your filters quarterly, and that really will really impact overall uptime and performance of whatever system it is that you have. And the other thing that is extremely critical is proper sizing. Now, in my eyes, we've been doing this for a couple of days now. You can't oversize a fan, right? Unless we have contaminants in the air, we don't want to try to push more air through there than we really need to. But if we have free air available, let's push as much air through it as we can and keep the enclosure cool. It's always going to be warmer than dew points, so we won't have to worry about it. Air conditioners, let's not oversize those. Heat exchanger, if we have surface area, it doesn't hurt to put a little bit larger heat exchanger on there. Oversizing the air conditioner is absolutely detrimental to the system, not only the air conditioner, but also the internal components. And then, best practice, let's perform some thermal audits on those critical systems, keep them up and running.
Sounds good. And just, hey, if you could walk us through how you do a thermal audit, that'd be very beneficial.
Absolutely. So it really is quite simple. And essentially we're looking at an enclosure And a very simple analysis of the size of the enclosure, how big is it, right? Let's get the overall surface area of the enclosure. What is our power supply available if we need a solution, right? Do we have 463 phase available, or we only have 230 available? And we want to take the temperature about 3 feet away from that panel. And then we want to take the temperature inside the panel with that process running. And what we're looking for again is that delta. We need to know what the temperature difference is with the system running versus 3 feet away. So example, day like today, down here in Arizona, it's 96 degrees. So let's just say it's 100 degrees in the facility, but as soon as I open the panel and I measure the temperature at the top middle of the panel, I'm measuring 115 degrees. I have 15-degree hotter temperature inside my panel than I do ambient temperature. I can plug that information into my selection calculator, and it will tell me how much heat is being produced to create that 15-degree delta, right? It's good to know if we are, just a standard type 12 or 3R system, or if we're type 4 system or 4X, because we want to make sure that we match the solution to the rating of that system. And then, again, we've discussed voltage supply. If we are in an outdoor environment and we need to maintain a minimum temperature, we want to notate that, because we can calculate if heating is required, how much heat would we potentially need for that, right? And then ultimately, we want to capture available mounting surface. If we have conduit penetrations on both sides of the enclosure and the only available place to mount anything, regardless of what it is, might be the doors, we need to note that, because that kind of helps us make a decision on what we can potentially recommend.
Perfect. Sounds pretty straightforward. And is there, I don't know if you guys have tools that kind of capture that from a legacy standpoint, that you can kind of capture all this data electronically and have a file of it?
So currently, we do not have a digital format to be able to capture this information. It is a PDF sheet, if you will, that we take that information and plug it into our little online calculator, and it will print out a PDF report for your file. That's the only way that we can actually do it at this point. So hopefully next year.
Yeah, they have an electronic copy or they have a print copy. That either way, at least there's the information there to capture that historical context. So
Yes,
that's important stuff.
Yes, sir.
Excellent. And I know there's the tool you also mentioned.
Yes. So the tool is designed to take the information that we've captured in an existing installation, or even in a new design, and we can plug that into the online calculator and give us a recommendation based off of requirements for that system. Now, when we're talking airflow patterns and thermal loads and equipment layout, that's on a more of an individual case by case basis, where I would get involved and kind of help you out, individually. We're starting to have challenges, or even from a design perspective, right? If we impede air conditioner supply airflow by more than, say, 25%, then we start to impact air conditioner performance, as well as overall stagnation and or air performance within that enclosure system. So there's some guidelines there for overall design.
Excellent.
Yeah, next slide.
Yeah, and I think with that, we're kind of come to an end. I appreciate the overall topic. Very interesting. Something that we have to think about and definitely, plan for. to your point, it's that maintenance, that ongoing maintenance to really get ahead of it so that it doesn't necessarily become a problem down the road. Very much enjoyed the conversation and the insights, John. So thank you very much. If you do
Absolutely.
have, I don't know if Mark's on the phone or Mark's on the call, if there's any questions, but trying to keep this, we're a couple minutes over the 30 minutes, but still important stuff. You can contact your account manager or inside sales representative. I know we have experts in-house that can help with the thermal audit, a gentleman by the name of Brett Bevers, as well as get HOFFMAN resources there to help out. So just kind of let anybody out there, if they want to kind of start to investigate this more for their facility. And with that, also just to let everybody know, coming up August 19th from 11 to 11:30, Matt Holstein with Schneider Electric, going to be going over a kind of a high level discussion on microgrids, combination of battery storage, solar, wind, potentially how do you integrate that all that into a facility and get some potential cost savings in that to mitigate some peak demand charges that we're starting to see from electrical standpoint. So this is a very, I put it, get a technical shallow dive, not a deep dive into it. So just to let everybody know that that's coming up in August. So again, I thank everybody that joined the call. And if you have any questions, you can reach out to us. Again, thank you very much, John, for your time.
Thank you, everyone. Have a great rest of your day.
You do the same.